Okay, you should have finished up your light bulb lab by now, so you should have a better understanding of series and parallel circuits and how those work. And in that lab, we asked you to measure the electric potential difference across several different light bulbs and batteries and devices. But we never defined what electric potential difference really is. So we're going to fix that today. We're going to go ahead and define that. And to be honest, it's a pretty tough concept to grasp. So the first thing we're going to do is we're going to have an analogy with something that we can see a little easier and something that we have some familiarity with. And first we're going to talk about gravitational potential energy because there are a lot of similarities between gravitational potential energy and electric potential energy. And once we understand electric potential energy, it's going to be much easier to understand electric potential difference. So let's take a couple minutes and let's talk about this figure on the right here. We have what looks like a book, and we have someone holding the book and pushing up on the book to move it to a higher height. And we say that at this low height, they have a low UG, and UG is just another way to say GPE. It's just gravitational potential energy. So you could just cross that out and put GPE because that's the term we use, okay? So we apply this force over a distance, so we know we're doing work, okay? So we're doing work on the mass to raise it from a low GPE to a high GPE. So when the mass moves, it goes from a low GPE to a high GPE. Now, let's take a look at a similar situation with a positive test charge down here. So right here we have our positive test charge, okay? And over here we have what we're going to call source charges. This is the source of the electric field. We haven't talked about fields, and you don't really have to understand an electric field. But what you should know is that the source of the gravitational potential energy up here is just the gravitational field due to the Earth, okay? So down here what we've got is we have our source charges that are the source of the electric field that we're going to experience. So we've got our test charge, similar to how we had our test mass here. And we're applying a force over a distance to get it closer to this source charge. Now, this is very similar to the force we're exerting up here because the test charge does not want to be next to these positive source charges, right? We talked about this in our electrostatics unit. Two positive objects will repel each other. So in order to get this positive test charge very close to these positive source charge, we have to apply a force. We have to do work over a distance to move these over, much like we had to do work over here to move this mass from an area of low GPE to high GPE. So what we say here is that when the test charge is very far from this source charge, it has low electric potential energy. The closer we get to the source charges, the higher the electric potential energy, and all this U means is energy, the higher the electric potential energy gets. So that's what we're doing, okay? So we say that we have a high electric potential energy when we're very close to the source charges. So what do we want to put in our notes to help us remember and understand that? Well, first thing we want to put in is that moving a mass to a high GPE requires work. And remember from our energy unit, work is just a force times a distance. We also know from our unit on energy that work is a change in energy. And in this case, work is a change in GPE. Okay. Similarly, moving a positive test charge requires work. Okay. Moving a positive test charge closer to positive source charges requires work. Now, what happens after? So this is the part that's really key. What happens after? Now, once the mass is moved to an area of high potential energy, if we provide a path back down, this book will naturally move back down, right? If we were to provide a path, say by removing their hand, this book would automatically go to an area of lowest or lower, certainly, gravitational potential energy. Same thing with our test charge. So our test charge, if we were to remove this hand and provide a path for the test charge to move, it would certainly move to an area of lower electric potential energy. Now, in both cases, okay, in the case of gravitational potential energy, the gravitational potential energy is dependent on the size of the book or the size of the mass. Down here, the electric potential energy is depending on how much charge we have, right? If we have just one, make up units here. If we just have one positive test charge, that's going to be a certain amount of high electric potential energy. But if we have, 10 times the amount of the positive test charge, then obviously our electric energy is going to increase. And that's not super convenient for when we're doing measurements because we really want to take the mass out of the equation here and the amount of charge out of the equation here, okay? So what we need to know about electric potential and gravitational potential is that the gravitational potential energy, okay, so the GPE, let me write that better. GPE depends on mass. Similarly, the electric potential energy depends on the Q, or the quantity of charge. So in order to get rid of that dependence, we're going to change up what we're looking at. So instead of looking at GPE, we could just talk about gravitational potential. And gravitational potential is simply GPE divided by mass. Similarly, electric potential is equal to the electric potential energy divided by the charge. So that's a more convenient way to look at those values, is to take out that mass or that charge dependency. Now, let's continue talking about our our analogy here. Gravitational potential energy really only has meaning when we define a location of height equal to 0, right? Otherwise, we can't really get a sense of, is this a high, is this low? So we have to look at, well, where is the height equal to 0? Where are we measuring from? Similarly, with electric potential energy and electric potential, we need to define a location of 0 potential, okay? So what we're normally going to see in a circuit is we're going to define one area where we have the lowest electric potential. And that's where the idea of electric potential difference comes in. So when we are measuring electric potential, we're really talking about measuring an electric potential difference. Now, in our GPE analogy, so in our analogy with our mass, we normally just pick a height of 0 somewhere. Right, so we pick a height equal to 0, usually at the lowest possible location of the problem. For our purposes in a circuit, we're going to pick the area of lowest electric potential to be the negative terminal of the battery. We're saying that the electric potential, and let me write that out, the electric potential. So the electric potential at the negative terminal equals 0. So that means that in our circuit, when we're looking at electric potential, we're looking at an electric potential difference across a component. So we're subtracting the value, and we're gonna look at some drawings in a little bit that's gonna make that a little more clear. Okay. So before we get that far, let's talk a little bit about units. Okay. So we know that our units for energy is simply a joule. So whether it's gravitational potential energy or electric potential energy, it doesn't matter. But we've said that electric potential is energy divided by the charge. So electric potential is going to be energy divided by the charge. Now we're going to measure charge in a unit called coulombs. We talked a little bit about coulombs when we looked at our electrostatic unit. So if electric potential is just electric energy divided by the charge, we end up with units of joules per coulomb, capital C. And this has a special name because, physicists like to give things special names. So we call that a volt, V-O-L-T. And that's exactly what you measured in the light bulb lab. You can also use capital V to stand for volts, okay? So what is the role then of the battery in the circuit? We talked about how that provides the oomph, and it really does. So the battery, what it does is it converts chemical energy into electric potential energy by moving charges from the negative terminal to the positive terminal. Okay, so it's not supplying the charges. Doesn't need to do that. Okay, it's not supplying the charges to the wires. It's simply taking the charges that are at the negative terminal of the battery, where they want to be. They want to be at the spot of lowest electric potential energy. That's where they want to be. And moving those charges, and remember those charges are positive, and we'll talk about why that is, because it kind of shouldn't make sense if you kind of paid attention in our electrostatics unit. So the charges are positive, okay? These charges, they want to be at the negative terminal. So the role of the battery is to move them against their will to the positive terminal, just like we saw up here, okay? So the positive test charges want to be down here, say at the negative terminal. The role of the battery is to push those charges to the positive terminal where they really don't want to be, okay? So if we were to draw this out, I don't know, I'm having a hard time with my screen here. So if we were to draw this out and we were to draw the battery and kind of look and see what's going on in the battery, this is the positive terminal, this is the negative terminal. And we have all these positive test charges that are just fine down here, but it's the role of the battery to force these guys up here, so that they all accumulate up at the positive side. So inside the battery, all the positive test charges are moving. Now what happens is that if we provide a path, and the positive test charges can't move down in the battery prohibits that, okay, due to the chemical energy. But if we were to provide a path from the positive side to the negative side, say through a wire, all those positive test charges would be happy to fall back down to the area of lower electric potential or lower electric potential energy. So that's what we see in a circuit. So let's take a look and see what you measured in the lab. And let's say we start with a 15-volt battery. You were asked to measure the electric potential difference across a light bulb. So let's just call this light bulb right here this resistor, and we drew it as a resistor, but it could be a light bulb just as easily. Let's just call that our first light bulb. And when you were in your lab, you would have hooked up one lead from the voltmeter right here, another lead from the voltmeter right here, and you would have potentially gotten an electric potential difference equal to 5 volts. That's because the electric potential right here is 15 volts. Now, how do I know that? Because we don't have an electric potential difference across a wire. And this is just a wire right here. So the electric potential difference here is 15 volts, okay, because of the battery. So anywhere along this wire, it's 15 volts. Well, if we got an electric potential difference across this light bulb of 5 volts, that means the electric potential difference right here, or electric potential rather, is 10 volts. That's why we got that difference of 5 volts there. And then here would be 10 volts, the electric potential again, and then maybe here was 5 volts, so that again we got an electric potential difference across that light bulb of 5 volts, and we will get the same thing here of 5 volts. Well, now look and see what the electric potential is right here. Well, we started with 15. We lost 5 and we ended up with 10. We lost another 5 and we ended up with 5. We lost another 5, and you should see that right here or anywhere on this wire, we end up with an electric potential of 0, which makes sense because we said that the location of lowest electric potential will be at the negative side of the battery, which is exactly what we saw here. Now, just to make sure we don't have any confusion as to why all these electric potential differences are 5 volts, this is only true because each of those components are identical. So we're in this little example, we're going to say that the electric potential difference across each component is the same, right? And in this case, 5 volts, because we have identical components. They're just copies of the same light bulb. That won't always be the case. That will not always be the case. So for instance, I could draw another circuit here and I could say, well, I've got a 15-volt battery, and then I could have a resistor here, and I could have a resistor here, and I could have a resistor here. And if I had a 15-volt battery, I could still end up with maybe this component had a 3-volt electric potential difference. This one has a 10-volt electric potential difference. And then what I want you to do is think about what's the electric potential difference have to be right here. Well, if we started with 15 and we lost 3, and then we lost 10 more, it has to be a 2-volt electric potential difference here, because I know I have to end up back at the battery with 0 here. We started with 15 at the top. We have to end up with 0 at the bottom. We can have the same discussion if we're looking at a parallel circuit. So this, you looked at this in your lab as well. And again, we're starting with the same 15-volt battery. So we know that if we were to measure the electric potential difference here and here, we would get 15 volts. So that means the electric potential must be 15 volts here, but 0 here. Well, now look and see what happens. We have a wire, a wire, a wire, a wire, a wire. I'm just going to go through this first loop first. And all I'm doing is going through a wire. And we know that we're not going to have any electric potential drop in a wire. That's perfect world, right? That's physics perfect world. You will have a little bit of electric potential drop in a wire, but nothing that we need to worry about, okay? So I'm going in through this wire, wire, wire. I get to here. The electric potential right here still must be 15 volts. And right here, if I look at this wire, 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 go to here, well, I know the electric potential there must be 0. That means that the electric potential difference across this component, this light bulb or this resistor, has got to be 15 volts. Well, I could have the same discussion for this second circle, right? We said a parallel circuit is just multiple circles. So I have this circuit, so now I'm going to go from here all the way to here. Again, I'm going to see that this must be a 15-volt electric potential, and this must be 0. So again, the electric potential difference across that component is 15 volts. And I bet you can see that this one must be 15 volts as well. Okay? So one thing to remember about our parallel circuit is that when you make one complete loop from the battery through the components, all the electric potential differences must add to the battery. So that's why if there's 15 volts here, I'm only going across one component. This must be the full 15-volt drop. Okay. Now, if we had a different circuit, and we'll try this, if we had a different circuit, and let's go ahead and try something a little different. So let's take this guy here, and we'll call this a 12-volt battery now. And this time we've got a resistor here and a resistor here. And we'll go ahead and we'll put just a wire here. And then we'll go ahead and put a resistor here and a resistor here. And then we'll just put a wire there. And let's say that I know that this right here has a 7-volt electric potential difference across it. So I know the electric potential right here must be 12 volts, and I know the electric potential here must be 5 volts. when I look at making a complete loop, I know that the electric potential has to end up here being 0. So when I do that, if I start here and I go 12 volts, this drop right here has to be a 5-volt difference. Okay? Same thing now, and this is only true because now I've got components that are not identical, right? I can have this 7-volt and this 5-volt. They're not going to be identical components in most cases. They could be, but they won't be. And then I can look here and I can say, all right, well, now I measure this electric potential to be 2 volts. Okay, and now I'm making this complete circle. So let's go ahead and draw that so that you can kind of see it. We'll use the yellow. So we're making this complete circle. And we can see that, well, we've got a 12-volt drop, or sorry, 12-volt supply. And then we're losing 7 volts. So we know 5 volts here. We lose another 2 volts. So hopefully you see that right here, that must be an electric potential of 3 volts. And that by the time we get back to the battery, that has to be 0. So I can tell that the electric potential drop right here must be 3 volts. So we're going to get a lot of practice with this kind of work, but that's the basics of what we're going to be looking at going forward. Now, as I said in the beginning, electric potential difference is not the easiest concept to grasp. So what we did at the end here of our notes is just put in a little kind of write-up for you to read independently on your own. I'm not going to read all this to you. Good Lord, that would be awful. But I am hoping that you will take some time and that you will read through this and take a look at these pictures to see if you can understand how this analogy between electric potential energy and gravitational potential energy help us understand what's happening in a battery. Okay, so go ahead, take a look at this, and then if you have any questions, you can ask in class. Have a great day.